Welcome back to the next video, everybody. Today, we're going to finally state Serre's conjecture. So a lot of the technical stuff from the last video, we won't really need again on a deep level. So don't worry about it if you didn't fully understand it. I'm not sure I do. Okay. So first of all, what is Deligne's construction? This is sort of a big motivator here. So theorem one, Deligne, let's let P be a prime and let's let N be an integer prime to P. Okay. And then we'll take an integer K at least one. We'll let F be a non-zero Hecke eigenform in M of nk epsilon over Fp bar. So this is where we're using some of the technical stuff. It's lurking in the background. We'll let A sub n be its eigenvalue for the nth Hecke operator T sub n. The theorem is that there's a unique semi-simple odd continuous representation, which we'll call rho sub f, from GQ to GL2 of Fp bar, which is unramified outside P and N, such that for all primes L that don't divide Pn, the Frobenius at L satisfies the property that rho of the Frobenius at L has trace A sub L, the L Fourier coefficient, and determinant epsilon of L times L to the k minus 1 power. So k is the weight and epsilon is the character of F. Moreover, if F has weight k at least 2 with coefficients in QP bar, there's actually a unique p-adic representation rho sub F of GQ with these same properties. Okay, so let's talk a little bit about the proof. We really just need the L-adic k equals 2 case. And I described that with references in chapter 1. We don't actually need the full power of this extremely deep theorem. This is known as Deligne's construction. So you should Google that phrase if you want to learn much more about this. There's a lot of course notes and presentations about it. Nonetheless, I'll say a little bit about where you might go to learn about this. Let's see, Gross's book has an elementary proof of the existence of the FP bar representation. So what was this book called? It was called Gross, a tameness criteria for some certain Galois representations or something like that. Then there's Deligne's paper itself, which I'll call DFM. You can also construct Shimura's book, Introduction to the Arithmetic Theory of Automorphic Forms, which I'll call SH for the k equals 2 case, which is the only case we'll need, but somehow that text deals in greater generality than we really need. The most succinct argument for the k equals 2 case comes from material covered in Diamond and Sherman, combined with a quick, kind of few facts from the Diamond-Darman-Taylor notes. I talked about this in chapter 1. In fact, kind of a more general result than this is proved there on the Jacobian. And I think it's an argument due to Conrad. Speaking of Conrad, if you can get your hands on it, which I have not been able to yet, but I understand that some people have access to this, and I'm working on getting it right now. Conrad's modular forms in the Ramanujan conjecture is also a wonderful reference for all kinds of stuff like this. This is like a fabled book that Conrad was going to finish and never did. There's been rumors that he's going to finish it since 2009 or 2010 at least, and I have not been able to find it, nor have I been able to find any indication that it's going to be finished. But there are drafts of it that I think some people have. Anyway, so there's all kinds of places you can go to learn about this. Okay, Serre's conjecture in a nutshell. Serre conjectured basically that any continuous odd representation rho from GQ to GL2 of Fp bar should be isomorphic to rho F for some such F above. Okay, I mean, what's the obvious thing to wonder, right? What possible levels, weights, and characters for F are you going to find if I give you such a rho? Okay, well, Serre's specific conjecture is that if rho is irreducible, there is an F with a certain minimal type, n of rho, k of rho, epsilon of rho. Okay, and you can see the Serre conjecture paper for this. We referenced this paper many times. All right, so what I'm going to try to do is just give you very briefly the prescription that Serre gave for n of rho, k of rho, and epsilon of rho, although we won't fully talk about the prescription for k. Okay, first of all, what you have to realize is that if P is a prime and I have a representation rho from GQ to GL2 of Fp bar, continuous representation, then because I have the discrete topology on the codomain, the image of rho must be finite. And a lot of people just say that and then don't ever verify it. I'm going to actually verify it for you. Okay, we know by continuity and the discreteness of our topology that the preimage of the identity, which is the kernel of rho, must be open, right? So by the definition of the curl topology, kernel of rho has to contain a set of the form the Galois group of q bar over k for some number field k, which means rho factors through the Galois group of k over q, where k over q is a finite Galois extension in q bar. Okay, well, that means rho is unramified at all but finitely many primes, because rho is ramified at p if and only if the image of inertia at p is not trivial, right? But that happens if and only if p ramifies in k. But from basic algebraic number theory, we know this happens only at finitely many primes. So basically, the statement that the image of this is finite boils down to a basic fact from algebraic number theory, which says that number fields only ramify at finitely many primes. Okay. So what is n? Well, the number n of rho is the Artin conductor of rho, ignoring the prime p. So what do I mean by this? Well, let L not equal to P be prime. Let I sub L be the inertia group at L of the Galois group of K over Q, which I'll call G, corresponding to some place of K above L, where K is as above. Okay. And let's filter I sub L by its ramification subgroups I sub Li. Okay, so there's I sub L0, I sub L1, and so on. What are these? Well, I sub Li is the subgroup of the decomposition of the chosen place above L, whose elements act trivial on the ring of integers mod the I plus first power of the maximal ideal. So why is IL0? Well, what is IL0? It's elements in the decomposition group that act trivially on the ring of integers mod the first power of the maximal ideal. Well, what's the first power of the maximal ideal? It's the residue field. And so we recover the usual definition of I sub L. Okay, so by bumping up these powers of the maximal ideal, you get the ramification subgroups of I sub L. Okay, to tell you what n of rho is, I just have to give you the L-adic valuation of n of rho for any L not equal to P, right? Here's the L-adic valuation of n of rho. VL of n of rho is the sum over I at least 0 of 1 over the index of I sub Li and I sub L0 times the dimension of V mod V to the I sub Li, where V is the two-dimensional FP bar vector space with the G action that admits rho, and where V to the ILI is just the subspace of V of I sub Li invariance as usual. And if you want a motivation for this formula, because I'm not going to motivate it, Serre has a paper that does this and proves some of the properties about it. I think also Cassels-Froehlich does a good job exposing some of the properties of this conductor. Okay, so that's N. So N is just the kind of the Artin conductor away from P. What is epsilon? Epsilon of P, I'm also going to tell you what the image of K of rho is mod P minus 1, but I won't specifically tell you what K is, but I'll give you references. Okay, first of all, recall that chi n bar from GQ to Z mod NZ cross denotes the mod n cyclotomic character. That's the character such that for all sigma and G sub Q and all nth roots of unity X and Q bar, sigma of X equals X to the chi bar of sigma. In other words, chi sub n bar governs the Galois action on the nth roots of unity. Okay. One can view a character of Z mod NZ cross as a character of the Galois group of Q just by composing it with chi sub n bar. Okay, and then Deligne's theorem, along with basic properties of cyclotomic character found in, for example, Diamond and Sherman chapter 9, imply that if F is an eigenform of level n, weight k, character epsilon over FP bar, then det of rho sub F, so the Galois representation attached to F, is nothing but epsilon times chi bar to the k minus 1 sub P. In other words, det composed rho sub F is just a character of Z mod PNZ cross, which is a group that's just canonically isomorphic to Z mod NZ cross FP star, right? And so under this isomorphism, the restriction of det composed rho sub F to the Z mod NZ cross part is just epsilon. And the restriction to the F star sub P part is just the chi bar sub P to the k minus 1. Okay, now I'm given that my rho is unramified away from Pn rho just by the definition of the conductor, right? Well, you can see I talked a little bit about this back in chapter 1, all the way back to the beginning. Now, by class field theory, the maximal abelian extension of Q is just the kind of this maximal cyclotomic extension. Q would join all these roots of unity, right? Well, that means I can view det of rho as a character on Z mod P to the NZ cross Z mod N of rho to the M cross for some N and M large enough. Okay, basically because the Galois groups of cyclotomic extensions are these groups of units. And so I've got like an N rho part to some power and a P to the N part for some N, because P is co-prime to N of rho. Okay, because remember, this is the Artin conductor away from P. Okay, well, we already know by the discussion above that this has values in F bar star sub P, right? Well, that means I can definitely take N to be 1. Perfect. If you compare the formula for the L-adic valuation of N of rho for rho and det of rho, and use a little bit of class field theory, you can actually see that you can take M to be 1 as well, which is kind of a relief. And so what will epsilon of rho be? It'll just be the restriction of det composed rho to this factor here, the Z mod N of rho cross factor. And I can also actually define for you the image of K of rho and F star sub P. It'll be chosen such that the restriction of det composed rho to the F star sub P part is nothing but chi bar sub P to the K of rho minus 1. So just choose the numbers that this happens, okay? The exact definition of K of rho is more complex. The details aren't too important for us. See the Serre conjecture paper and also Cornell Silverman Stevens chapter, page 213 in chapter 7. Okay, so let's state the conjecture. Formally, what does Serre's conjecture say? Let's let PB prime and let rho from GQ to GL2 of FP bar be a continuous, irreducible odd representation. Then there's an eigenform F in S of n rho, k rho, epsilon rho over FP bar, such that rho is isomorphic to rho sub F. So that rho is modular, with the associated cusp form being of the level, weight, and character that we just described above. Okay, why cusp form actually though? Let's make a couple closing remarks. If you consider the action of the Hecke operators on the cusps, you see that if F is a non-cuspidal eigenform, then rho F is just reducible. Okay, so but we're dealing with an irreducible representation, so in the conjecture, we can just demand F as a cusp form. Okay, the other thing is, if you read the Serre conjecture paper, you'll see that Serre's original conjecture is not the same as the one stated here. Because there, in that paper, modular forms over FP bar are just defined to be those that are obtained by reduction mod P of modular forms over Q bar. So kind of the usual modular forms you're comfortable with. That is, Serre originally defined a cuspidal modular form over FP bar of type nk epsilon with n and p coprime and k at least 2 to be any element of the image of the reduction map from S nk epsilon tilde over zp bar to S of nk epsilon over fp bar, where zp bar is the integral closure of zp and qp bar. And what is epsilon tilde? It's the Teichmuller lift of epsilon. It's a character from z mod nz cross to zp cross sub p. And it's just a character that induces epsilon when you reduce, and it has the same order. We won't get into Teichmuller characters here. Okay. But the problem with this definition, Serre's original definition, is that actually these reduction maps, believe it or not, are not surjective. And so Serre himself later acknowledged this and suggested modifying the definition of mod P modular forms to use the definition we're currently using here, which involves some of that technical theory from last time. Okay, so we will start looking more into Serre conjectures next video, and I'll see you then, and thanks for watching.